spectral investigate.
Okay, thank you very much. So the title of my talk is Some Topics in Spectral Graph Theory. It's maybe one or two topics, I don't know yet how it will go. So what I will start with is an introduction. So I suppose that not so many people here will know what in spectral graph theory really means, and then I will give some recent results. Okay. So for me, the graphs in this talk will be simple and undirected. So everybody knows what I mean by simple undirected graph, so that is what the point that I will consider. So if a graph C is V, E, and we consider E always as a subset V should 2, the two subsets of V, then we can make the adjacency matrix A, so such that A, X, Y is either 1 or 0, and is 1 if X, Y is in E, or you can say, I will usually write X is adjacent, right? So this is yes, and otherwise 0 otherwise. That means either X is Y and then they are not adjacent, or X is different from Y and then they should be not adjacent. Okay. So what we are going to do is looking at the spectrum of C. And what is that? That is defined as a spectrum of A. And this is well defined. I mean, because all adjacency matrices are similar to each other. You have to worry a little bit about that, but that is very good. So, and we say an eigenvalue, lambda is eigenvalue of C if it is an eigenvalue. Yeah. Of A, yeah. So. So spectrum is the eigenvalues plus the multiplicity. So the spectrum is lambda 1 greater equal to lambda 2 greater equal to lambda n, where lambda I is an eigenvalue. Yeah. Okay. Does this make sense? You have to worry about that a little bit, no? Because this only makes sense when we know that the eigenvalues are real. You have to worry about that. So, of course, A is symmetric. 0, 1 matrix. So therefore, eigenvalues are what shall we say, real. You can say also algebraic integer. I'm not sure whether everybody knows what an algebraic integer in this audience. Does everybody know? It's because this is a matrix where all the entries are integral, so therefore the polynomial of the matrix is a monic polynomial with integral coefficients. Okay, so the first thing you can see is a trace of AI is a sum lambda I to the power, I should say, to the power I. I is 1 to n. No, my j is 1 to n. Yeah, that is what you learn in linear algebra. But this is very useful because what is a trace of A is 0, but that is also the sum j is 1 to n. Yeah? So the sum of the eigenvalues must sum up to 0. That is what it says. What is trace of A squared? You can say, yeah, that is a sum. J is 1 to n lambda j squared. But on the other hand, this is a sum of the degree of x, where x is in V. Because what is A squared xx? My claim is that it's exactly the degree of x. Yeah. So, but this is, we learned this also in graph theory, that this is 2 times the number of edges. So from the spectrum you can easily see how many edges a graph has. And this has to be an even number. What about, then you can go, the trace of A to the power 3. Is on the one hand, we can say that it's j is 1 to n lambda j to the power 3, but this is 6 times the number of triangles. And G. But then, what about trace of A to the power 4? Yeah, we get still the same number with here lambda I to the power 4, but that's not, what is this exactly? That's not so clear, because, and you cannot say that it's something like 4 cons or something like that, because you have to be very careful. Look at the following example. Look at this example, This is one. These are 2 graphs. What is the spectrum of this graph? Can somebody tell me? This is 2 regular graphs, so this has an eigenvalue 2, minus 2, because bipartite, and 0 to the power 3. This is fairly easy. This is a bipartite graph, so this is this has to have eigenvalue 2 and minus 2, but then you see that the rest has to be 0, because once you have the 2 and the minus 2, you are done because of this formula. Because you can easily add, how many edges does it have? 4. So in total this will be 8. The sum of the squares must be 8. And this is 4 plus 4, and then the rest has to be 0. So, but by accident this has also the same spectrum. If you don't believe me, you calculate yourself, please. This is a bipartite graph, so you know that the last eigenvalue is the same as the second last eigenvalue. To find the last eigenvalue, you look at the matrix 0. What shall we do? 4, 1, 0. Because if you make this, what do I do? What I mean is here, I want to make this as 1. I'm sorry, do we have some eraser? Are there some erasers?
Howard's?
That was Oh, it is towers, okay. Okay, so I better do this away. Huh? So if you look at the 4 vertices in the outside, you see that. So I can make this. Also, you can look at this partition 4 against 1, and then you see here 4 vertices and one vertex, and then you can look at this. Every vertex has exactly one neighbor there, 0 neighbors in itself, and this one neighbor has exactly 4 there and 0. And then you can associate this with this matrix, and then you can show that the eigenvalues of this matrix are eigenvalues of this graph. But I'm not going into details here, but once you know this, the eigenvalues of this one is clearly 2 and minus 2. I don't have to calculate it because the sum is 0, of the sum of 2 eigenvalues 0, and the determinant is the square. The product is minus 4, so yeah, and there must be 2 and minus 2. That's one way to see this. That. Okay, but this says, so I mean, but the reason why I draw this is here they have a foreground. This graph has no foregrounds, but they have the same spectrum. So they are called a co-spectral graph. Yeah. But you can also see connectedness you cannot see from the spectrum. Because this graph is disconnected, it has 2 components, and this has 1 component, and they have still the same spectrum. Okay, so an interesting question is, what can you see from what kind of combinatorial properties can you obtain from the spectrum? Another question will be, yeah. So an open question is the following. Let me AN be the number of graphs C. On C has n vertices and determined by spectrum. Yeah, and let Cn be the number of C or has n vertices. And then you can ask, what is the limit, n goes to infinity, of An to Cn? Yeah? And I think still an open problem that this is 1.
So is it labeled graphs or?
No, unlabeled graphs. So these are unlabeled graphs. I'm sorry, you're right. These are unlabeled graphs. So you consider isomorph graphs as the same graph. Yeah? I don't know, for labeled graphs probably doesn't make so much difference, I would guess. But you have to be a little bit more careful there. I didn't think whether this should be unlabeled graphs. And some people think that this should be the case, but nobody knows. But this is not so stupid question as it sounds in first instance. Why is it? Why is it? Can it be interesting? The question is, if I have 2 graphs C and H, when are they isomorphic? How can I compute it? That seems to be not so easy. But if they are isomorphic, then they have to have the same spectrum. Yeah? But is it difficult to check whether they have the same spectrum or not? It's not difficult. It's polynomial time, about n to the power 4, to check that they have, because you can check, you need to check whether the trace of AI of G is a trace of AI of H. If you have the graph G and H, then you only have to check whether the traces are the same for I is 0 to n minus 1. Yeah? And so and to check that is a fairly easy way, because once you know that the traces are the same because of this formula, that lambda I is this, you get that the same, you have the same spectrum. From the spectrum, from the traces you get the same spectrum. So, so if I have time over, I will talk about this a little bit later. I will look at this kind of problems later today. But before I want to do that, okay. Another question is, I said, can you check? Yeah, you cannot check whether a graph is connected or not connected. You cannot see that from the spectrum. Can you see whether it's K regular? Can you see whether it's regular or not? Regularity. Can you check regularity? Whether the graph is regular or not? So you say, yeah, but that is fairly easy, no? What you can show is, suppose that you see has eigenvalues lambda 1 with lambda n vertices m edges, then you can say then lambda 1 is always greater or equal to 2 times m over n, and equality even only if G is K regular, is 2m over n regular. So this shows that, that it is determined by spectrum. Why? Because m, you see m is determined by the number of edges, or by the eigenvalues, the squares of the eigenvalues. And n is the number of eigenvalues. So you can see from the spectrum whether a graph is regular or not. And the proof of this is fairly easy. The proof says, look at A, J, transpose J. What is this number? That is 2 times m. Because you count every one exactly once. And it has two m1s in the A. And then you can ask, but if I divide it by this one, then this is this. But we know that this is always less or equal to lambda 1. Because lambda 1 is its largest eigenvalue, and I can always decompose J as a sum of eigenvectors. So then I see that easily, because A is symmetric, it's triangularizable. So we don't have diagonalizable. I'm sorry, it's diagonalizable. So we can get a basis of eigenvectors, even orthogonal basis of eigenvectors if you really want. But you get a basis of eigenvectors, and using that, you see this immediately. And what happens if equality holds? Then the all one vector must be an eigenvector. But if the O1 vector is an eigenvector, it must be K regular. Huh? So that is all the proof. It's not so difficult. So what does this say? Is that regularity? Yeah, you can see it from the spectrum. But if it's K regular, you can also see how many connected components it has to have, because that would be then the multiplicity of the last eigenvalue. If it's K regular, then the number of connected components is exactly the multiplicity of the last eigenvalue. Okay, that's all fairly easy. So. And less trivial so a theorem what you can also say in spectral graph theory is the following theorem by Cameron, Goodhals, Seidel, and Schultz. So what they showed is a regular graph with smallest eigenvalue -2, at least -2, I'm sorry. With small eigenvalue is either, there's three cases. It is a line graph. A line graph, that means it is a graph which you obtain by taking the edges of another graph, and two of those edges are adjacent if they have a common endpoint. Or it is the cocktail party graph. The cocktail party graph. Graph that means really the complement of the complement K to M and then the complement. So you take M edges, and then you take the complement. That is the cocktail party graph. Or this is not always then one. I mean, okay. Or you have that N is at most 28. Yeah. Either you have one of the three cases, either this cocktail party graph or line graph, or N is at most 28. So this, in a sense, characterizes line graphs. Yeah? Because this is fairly easy to see, and this is also easy to check, and the rest you must have a line graph. So that is, so -2, yeah, then you can do, yeah, if you see that the smallest eigenvalue at least -2, then you know it's exactly always a line graph.
Line graph of a regular graph?
Of a bipartite graph where the two different, what is semi-regular or biregular, I never know what is, if you have a bipartite graph, say, G with color classes. Say R and B, and then you have the degree of X only depends on in which color class it lies. Yeah, so you have two color classes that are, these are any edge has a red and a blue vertex as endpoint. That is what you can say. Yeah, for example, K23. with K23, that is this graph. And what is the line graph of K23? That is. So you can see that this vertex has how many neighbors? 1, 2, 3. Yeah? So this is a 3 regular graph. Eh? And you see that these 2 vertices have degree 3, this 3 vertices have degree 2. So this is called a semi-regular. Some people call this semi-regular, other people call it bi-regular. So, but I believe that semi-regular is a better name because it's not less than regular, so it must be.
So any line graph which is regular.
It comes from either a regular graph or a semi-regular graph. Bipartite and semi-regular. That is what is easy. You can also, that is fairly easy to see. Okay. So for the rest of my talk, I will concentrate on the properties of lambda 1. I will concentrate on lambda 1, and what is in fact is, and this is quite important, is let C be connected, then lambda 1 is greater or equal to minus lambda n, and equality if and only if C is bipartite. And this is not so easy to prove. This follows from the Poisson Frobenius theorem. So the proof is not so easy. That has to do with certain what this says about any integral matrices. You can look at the integral matrix and look at the lastest in absolute value, the lastest eigenvalue of the matrix, and that you can show that is always a real number. That is what the Perron-Frobenius theorem says. And then it says also, if it is, you have to look at whether the underlying digraph is strongly connected or not. And if it's strongly connected, then you know that is all then minus that number doesn't occur. Then all our eigenvalues have in absolute value less than lambda 1. That is what the Perron-Frobenius theorem says. But if you apply it to our setting, then this is the Perron-Frobenius theorem. And the lambda 1, this number, is called the spectral radius. Of G. And usually we call it rho instead of lambda 1. So the spectral radius is the last eigenvalue of the graph. So then, so the next topic is we want to find a lower bound on the spectral radius. Yes, but this is not so. Yeah. So suppose that you see a connected graph on n vertices. Then the graph with smallest spectral radius if you look at all the connected graphs on n vertices, what is the smallest? If you look at all these graphs, which one has the smallest spectral radius? No, not the Euler part. The part of length n minus 1. Pn. Yeah, that is the smallest. Yeah, that's easy. That's not so difficult to prove. I mean, it's what you expect. But what about if you assume that C is connected n vertices and diameter d? Of course, this must be smaller than equal to n minus 1. What can you do then? So this kind of problem came from computer science or electrical engineering. The reason is, if you have a computer network, then you wanted it to be as resistant to virus attacks as possible. And then it was shown that how lower the spectral radius, how better it is resistant to virus attacks. That was shown a few years ago. So that is where this question came from. And so that is what we are going to solve today. What can we say about this number? So the first result is by Van Dam and Kooi. So what they did is they looked at D is 2. And then rho of G is always greater or equal to square root of n minus 1 with equality if and only if this is a star graph on n minus 1 vertices or a Moore graph. And for the Moore graphs there are the pentagon, the Petersen graph, the Hofmann-Singleton graph, and this has 50 vertices. I cannot draw it on the blackboard, I'm sorry. The pentagon everybody knows. The Petersen graph I think everybody knows. The Petersen graph. One way is to this. That's the Petersen graph. And the Hofmann-Singleton graph was discovered a few years, I think in the 1970s or so. And then there exists a possible graph on 3,250 vertices. This valency degree is 57. And nobody knows that this graph exists. And this is already open for probably 30 or 40 years. So
that's one of the Moore graphs?
this could be a Moore graph. But nobody knows whether this does exist. If it does exist, it must be quite ugly.
But what is a Moore graph? How is it?
A Moore graph is, so I will need that. If you have a k-regular graph, then you can say diameter d. So you have a connected k-regular graph with diameter d, then the number of vertices is always bounded by 1 plus k times k minus 1 plus k minus 1 d minus 1. And equality is called a Moore graph. This is called a Moore bound, by the way. Yeah. So equality is called a Moore graph, and it is known that for diameter 2, it is either the pentagon, the Petersen graph, the Hofmann-Singleton graph, or some strange graph on 3,250 points. Or for larger diameter, it's only a polygon, the odd cycle. For D at least 3, then it was shown by Banai and Ito, and independently by Damerel. That is okay. So that is what Van Damme and Kooi did. So then we try to extend this theorem to any diameter. And how can you extend this theorem to any diameter? So the theorem is by Xiao Li. I don't know, do I write his name correctly? I don't know. Van Damme and myself. Is what we showed is that rho g is at least n minus 1 to the power 1 over d. So you change the half here to 1 over d. So for d is 2. It's a spectral radius. C with spectral radius with diameter d. Valency of the n vertices, spectral radius. I'm sorry, rho is rho c, then rho c is at least n minus 1 over 1 over d. And equality if and only then d is at most 1 or 2. And then you are in this case where you have equality here, or for d is 1, there's nothing to be proven.
So the inequality is never tied, is this?
Yes. But I will discuss that also later. How good this bound is, I will discuss that later. But the proof is very easy. How would you prove this? Let's think about a to the power d, j transpose j, j transpose j. This is 1 over n, the sum over x in v, the number of paths of length, I should say not paths, walks, I'm sorry, of length d minus 1 starting in x. But now my claim is that this is always greater or equal to this is always, and then this is n minus 1. But you can say, yeah, I will show later. So I will show that this is always greater or equal to this. The normal walks of length d minus 1 starting in x is at least n minus 1. And once you have shown this, then this is easy. But this is, by similar reasoning, this is the row of a to the power d. But that is rho a to the power d. And because this is polynomial a, so you don't have to worry too much about the rows. So then you get this immediately. So the only problem is, this. But I don't know how to do this exactly because it's fairly easy. But how do you do this? I will do an example of diameter 3, say, because once you understand the diameter 3, then you understand any diameter, I think. So diameter 3. So you take x, then the neighbor of x, the y which I say to x, and then you can look at n2 of x, and say n3 of x. So this means the vertex is at distance 2. From x, and this is clearly from 3. So now we take a vertex say y in here. So what we do is, here we have a part of length 2, but we return to there. For a vertex here, this is also a part. That must be a part of length 3. And for a vertex here, what do? You go here and then go back and go back. So you see that for every vertex there is a walk of either this kind or this kind or this kind. But you can see that for diameter 3 you can do much better. Because I only look at this one and back and this one. But I can go this one and go backwards and take any other vertex. So you can see that for the paths which have endpoint in the neighborhood, they can take, instead of the number of the degree of x, you can take, instead of degree of x, degree squared of x. That always will work. So that you see that this is never tight if the diameter is 3. Because then there has to be a vertex of degree at least 2, and then you get at least something else. So that is the idea where you show that the normal walk of length d minus 1 starting x is x at least n minus 1. So, but you see that this seems to be very stupid. I mean, it seems not. It seems that there must be many more parts of length d minus 1 than I count only very special kind of walks. But I didn't count all the walks, so I mean that seems to be a little bit bad. But what is true is that this bound is not so bad. So this bound is not so bad. What you can look at is, you can look at what shall we call rho n is the minimum of rho of C, where C has diameter D. Maybe I should say here also D and D. So C has a diameter D and vertices. So you could look at the, maybe I should not call this a minimum, or it should be maybe an infimum. Although there are only finite graphs, so you can also call it minimum. Okay, but then you can think about what is the limit n goes to infinity. Or maybe you should look at the lim inf or lim sub, if you like lim sub or lim inf. So what do you want? Rho n d over n minus 1 to the power d 1 over d. Yeah, you can look at this number. And the conjecture is that this is 1. What we can prove, we proved. So that this lim sub n goes to infinity, rho n comma d over n minus 1, 1 over d is smaller than 2. So that is what we showed. We constructed an infinite family graph where this is smaller than 2, so then you get that this is 1 equal to 2. And it has also to do with the Moore graphing I talked about earlier. So okay, that's what. Okay. So this is an I think that so there's some relation to some extreme graph theory as well. So what extreme graph theory problem? So now the problem is it's a diameter degree problem. So I fix delta, I fix the integers. Now I ask, and the delta at least 3, the doesn't matter too much, the at least 1 maybe. Then you can ask, what is the maximum number of vertices a graph, so we call this n delta d can have a graph can have such that the maximum degree is at most delta and the diameter is at d. And I have said the whole number of the Moore graph says, the Moore bound says n delta d is roughly less than delta to the power d. You have to worry a little bit. Is this exactly? You have to, yeah. You can show that this is true. Yeah, is it d minus 1? No, d, yes. Yeah. And then you can ask the question, what is the limit, or lim sub, or lim inf? What is lim inf? So is it the maximum number of vertices, or is the minimum number, the maximum number of vertices? So what you can look at is, what you should do is maybe lim sub. So you want to look at the delta goes to infinity of this number. You fix d, and you want to look at this number. And the conjecture by Bolobas that this limit is equal to 1. And if this conjecture is true, this implies this conjecture. So this is somehow the spectral formalization of the theorem of this conjecture. I should say conjecture, not yet proven. I'm sorry, that is in his extremograph theory book. So he conjectured this, and this is shown to be true for d. True for d is 1, 2, 3, and 5. And that's all what is known about this conjecture. But if this conjecture is true, this implies this conjecture.
So they have something like limit is less than something?
So the limit is always 1,
okay.
most 1. Yeah, and now you want, so this should be lim inf. I mean, you have to say here limit, but if the limit is then it's also lim inf. I think that is all I would like to tell you today. Okay, yeah.
Thank you.
Thank you for your attention.
Any questions?